Thank you, Jerry, and once again, thank you, NewEra Software, for sponsoring the zExchange in general, as well as these sessions that we're doing on cryptography. As we discussed in December, the plan for 2015 was to go back and pick up some of the basics, starting with the intro to crypto, and then maybe go back over the hardware again. Cryptography has a lot of buzzwords and acronyms that you've got to hear some of these multiple times before they start to sink in. So we were going to go back and revisit these. However, with the announcement of the Z13 in January, there's some new material there that needs to get incorporated in, but until the documentation becomes available in March when the Z13 GAs, we really don't have enough details yet. So today we are going to do the intro to crypto, but we're probably going to slip those hardware presentations until at least March when more of the documentation's available. So with that, we're looking at or looking for a topic for February. If there's something that we haven't covered before, or something that you think we need to recover and go over again, we are looking for suggestions. So if you can send a note either to Jerry or to me, my email is there on the cover page with suggestions for topics. We'll look at doing something different in February and then coming back with the hardware and covering the hardware again in March. So with that, let's go to slide 2. And what we're going to cover today, we're going to start out with some background, just some basic introductory stuff, and then we'll get into the cryptography functions that are available. Typically, when you think of cryptography, you think of scrambling data, and that's a very important piece. But there are some other things that go into cryptography, some things you need to understand so that you can better leverage the technology that's available. So we'll cover some of those other algorithms, hashing and digital signatures and such. And then there's one slide toward the end to talk about the Z13. There are a number of things that are new that at least I'll give you a heads up on so you'll know what's coming. So with that, let's get into things. Let's go to slide 3. So cryptography, as defined by Merriam-Webster, is secret writing. That's taking data and scrambling it, encoding it so that you can't see the original data. What you see looks like garbage. And the trick is knowing that you've got the right garbage. If you encrypt data today, it's important that next week or next month or 10 years from now, you be able to recover that original data. Know of an insurance company whose data retention policy is 100 years. And the idea here is that they may cut a policy for a newborn baby today, and that data is going to need to be maintained for the life of the baby. So the retention period can be quite long. Now, the technology is going to change over that 100 years or so, but you need to be able to recover the data at some point, and as you move from technology to technology, you'll need to be able to decrypt and re-encrypt that data. So it can span a long period of time. Um, One of the other definitions that's out there talks about the fact that it's kind of a science and an art. And there is a lot of heavy math, and we'll see some of that as we get into the discussion today. But there's also an art to it in terms of making sure that you don't compromise things as part of the process of protecting the data. It's actually fairly easy to leave a key laying around, maybe in memory somewhere. And if you do, that could compromise the data. So there is a little bit of an art to it as well. Let's go to slide 4. So have you ever considered what you need to run your business in terms of trust and integrity and confidentiality? Um, Trust and integrity in that, are your business transactions valid, or is the amount of the transactions the correct amount? Are they being recorded properly in your financial statements? You also had the issue of confidentiality or the secrecy of data. Obviously you need to protect things like trade secrets. You also want to protect things like your customer list, the transactions that you execute. You don't want somebody to be able to snoop and see that, one of your customers is buying, gearing up and buying lots more product or whatever. You've also got to worry about the the privacy of data, not just your customers, but maybe your employees as well, and things like social security numbers and bank account numbers where their paychecks are deposited. So you've got to provide confidentiality in a number of different aspects. And then the other one, which gained a lot of attention with the PCI requirements and all, is the accountability and the auditability of your data. Um, is it a valid transaction? Can somebody capture a transaction and then replay that transaction multiple times so that where they authorized you to to charge their credit card for $1,000, if somebody could capture that and replay it, you could take $1,000 multiple times from that customer. So there's this accountability of the transaction. Are they the valid and accurate transactions? And then auditability is, if there is a breach, if there is a problem, can we go back and look and say, where did the problem come into play? How did the bad guys were they able to introduce these? So cryptography can help with all of these, not just the confidentiality, but the integrity of the transactions, as well as the accountability and the auditability. So let's go to slide 5. There's basically 4 types of cryptographic functions that are available. There's the data confidentiality, the scrambling and the unscrambling of the data. And there's 2 types of algorithms. There's symmetric algorithms and there are asymmetric algorithms. And we'll get into those a lot more in a minute. There's the data integrity functionality. There's a couple different flavors of that. There's modification detection. Can I tell that a message has been changed, whether accidentally or intentionally? There's message authentication. Can I tell what the source of a message is? Does it really come from who I think it came from? And then there's the concept of non-repudiation. And that's the idea of, can I deny having authorized a transaction? So in our online world today, where I may go on the internet and go to a catalog store and order a product, and maybe I order 1,000 widgets and I provide my credit card information to charge that transaction. Of course, that catalog store does not want me to be able to come back later and say, no, I didn't authorize that credit card transaction. I didn't submit that transaction. They don't want me to be able to repudiate the transaction that I initiated. We'll talk more about that in a little bit later on. The third bullet there, or major bullet there, is our financial functions. So that's ATM PIN processing. ATM PIN processing is built on symmetric encryption, but there's a whole lot more that goes into it. There's a lot more sophistication there, because when you stop and think about it, a PIN is only 4 numeric digits, and so there's not a lot of possibilities for values there. There's 10,000 possibilities. So there's got to be some more sophisticated secrecy and confidentiality around protecting those pins. And we'll talk more about it toward the end of the discussion. And then the last major bullet on there is key security and integrity. Now, you're not going to go out and buy a cryptographic system just so you can manage keys. However, key management, key security is an integral part of your cryptographic environment. And if you can't protect your key materials, if you don't have integrity of the key material, you don't effectively have a cryptographic system. It's kind of understood in cryptography that the good guys have access to the keys, the bad guys don't. If that gets compromised, your cryptographic system is going to break down. So I think one of the things that you'll see as we talk about the hardware and the software that's available in the IBM environment, it does provide a tremendous amount of key security and key integrity to manage your cryptographic environment. So let's get into data confidentiality on slide 6. Again, the first type of algorithm is what's called a symmetric algorithm. And with the symmetric algorithm, both parties, both the encryptor, the sender, and the decryptor, the receiver of the message, have access to the same key material. They are using the same key on both sides of the conversation. So as a sender, if I want to send you some data, I'm going to take a key and use that to encrypt the data. I'm going to send you that ciphertext. I also need to send you a copy of the key that I used. That you have to have that exact same key value that you can use to apply to the ciphertext and recover the clear text value. So one of the advantages of symmetric algorithms as compared to asymmetric is that they are very fast. They're very efficient. Now, they cost resources. It takes resources to encrypt the data, but compared to asymmetric, they are significantly more efficient, significantly faster. The downside of the symmetric algorithms are the key distribution issues. That is, if I wanted to share a message with everyone that's on this call, I would have to have a unique key for each person. If two people had the same key, they could encrypt or decrypt each other's messages. So I've got to have a unique key with every person on the call. And maybe, if we're doing really good security, if you want to send me data, we're going to have another key pair. So the number of keys that I have to manage to exchange messages is twice as many as the number of people on the call. And if I'm doing good cryptographic hygiene, then I'm probably going to rotate those keys periodically, change the keys periodically. So whatever that period is, whether it's weekly, monthly, yearly, now I've got to manage even more keys. So key distribution, getting that key material to you and managing the keys in a symmetric environment, it makes life a little bit more difficult with symmetric keys. Let's go to slide 7. There are a bunch of symmetric algorithms out there. There's literally hundreds of them. Some are very sophisticated. Some have been around a long time and have been vetted and are considered to be very secure. Other algorithms might be newer, may not be quite as secure, maybe just haven't had time to validate the security. So up at the top, we have DES and triple DES, and we'll talk about how they differ in a minute. And we have AES, the Advanced Encryption Standard. Those are the algorithms that are supported in the IBM cryptographic hardware. There are other algorithms that are implemented, some in IBM software. For example, Blowfish is implemented with System SSL, so it's provided in software. Some of the other algorithms maybe aren't quite as secure. Skipjack got a lot of attention in the Clinton administration and maybe weren't considered quite as secure, so they haven't been as widely accepted. Other of these algorithms might be proprietary. That is, there's license agreements required if you want to use them. So they may or may not be generally available, maybe only from the people that invented the algorithm. So there's a bunch of symmetric algorithms available. We're going to focus on triple DES and AES today. On slide 8, the DES algorithm was actually developed by IBM back in the 1970s. There was a Project Lucifer internally to IBM, and the Project Lucifer came from the idea that when they talked about what they wanted to do, they wanted something that was devilishly difficult to implement or to protect the data. So Project Lucifer was submitted, or DES was submitted to the federal government as a proposed standard, and it was eventually accepted. Now, what DES does is it will take an 8-byte key value and apply that to an 8-byte message to protect the data. And we'll see on the next slide that what goes on in that algorithm is fairly complex, but very simply, you're applying an 8-byte key to an 8-byte block of data to create some ciphertext. So let's look at slide 9. And what happens within the DES algorithm, there's actually multiple iterations, 16 iterations of moving data around, substituting data, permutations, shifting bits around. So for example, substitution. If the input text, has a hex 62, there might be a substitution table that says the hex 62 gets replaced with a hex 09. So there's some substitution that's going on. You're flipping half of the message, so the left half of the message gets swapped with the right half of the message, and the right half, there's these scrambling operations are going on, these permutations are applied, and again, that's repeated 16 times or iterated 16 times just to encrypt that 8-byte block of data. So it's some fairly complex math that's going on to scramble the data. On slide 10, to decrypt the data, you basically just reverse the process. So that switching of data, the left half and the right half is simply reversed. The substitution tables are simply reversed, so that hex node 9 gets replaced again with the hex 62 value. Again, you're applying that same 8-byte key to the 8 bytes of ciphertext to recover the clear text value. Now, you may have heard that DES has been broken, that you shouldn't be using DES, and that's true. It's not exactly true that the algorithm has been broken. There's no magic algorithm that you can take DES data and run it through the algorithm and recover the original clear text value without the key material. However, what is true is that machines have gotten so fast, the technology has gotten so fast that you can do what's called a brute force attack. And basically, that just means you can try every possible key value to recover the data. There's an industry consultant named Bruce Schneier who's written several books, and he went on record some years ago to say that it's within the capabilities of most governments and even many large corporations to build a specialized piece of hardware to perform a brute force attack and to recover a key within less than 24 hours. So back in the 90s, the cryptographic world saw that machines were getting faster and faster, and this brute force attack was becoming more and more feasible. They started looking for alternatives and ways to make the encryption stronger. And what they came up with was triple DES. So on slide 11, triple DES basically just uses the DES algorithm, but by using a longer key, they execute that algorithm 3 times to provide more security. So you start out with the same DES algorithm and you take the first 8 bytes of a 24-byte key and apply that using the original DES algorithm. You apply that to 8 bytes of data and you come up with some ciphertext. But instead of using that ciphertext as your output, you repeat the process. This time you perform a DES decrypt operation and you use a different 8-byte key into this intermediate operation. That creates yet some more ciphertext, but instead of using that as your output, you apply the DES encryption algorithm once again with a third 8-byte key to create even newer ciphertext or different ciphertext. And that ciphertext is the output of your triple DES operation. So effectively what you've done is you've used the DES algorithm, but instead of using an 8-byte key, you've used a 24-byte key. And with the 24-byte key, that means that brute force attack is no longer feasible. Bruce Schneier, in the same book that he talked about being able to build a specialized machine that would break DES encryption, he said there's probably not enough silicon in the universe to create a specialized machine for breaking 24-byte triple DES encryption. So this is considered much more secure. And on slide 12, to recover the data, you just reverse the process again. So you take that final ciphertext and you reverse the operation. You do a decrypt on that using the third 8-byte key. And then you take that intermediate result and perform an encrypt operation using the second 8-byte key. So you're reversing the second step. You take the output of that operation and now you reverse the first step. You perform a DES decrypt with the first 8-byte key, and that brings you back your original clear text data. So that's considered much more secure, much stronger than DES encryption, and you should not be using DES today. You should be using triple DES. Now, NIST has gone on record as saying that, given the pace of Moore's law, given the pace of improvements in technology, they think triple DES encryption will be secure until about the year 2030. And so you got kind of a Y2K problem here that, out some point in the future, you're going to have to move off of triple DES to something stronger. And in the early 2000s, the federal government started looking for alternatives to triple DES encryption, and they came up with what is now called the Advanced Encryption Standard. Let's go to slide 13. Oh, no, before we go there, the beauty of the triple DES algorithm was that it provides upwards compatibility when people were transitioning from single DES to triple DES. Let's go to slide 13. And with triple DES, you could perform triple DES encryption. So you upgrade your technology, you can support triple DES. You could still communicate with your partner who is limited to single DES. And you could do that by using the same 8-byte key for all three parts of your 24-byte key. So you could encrypt your data with an 8-byte key and create some ciphertext. And instead of stopping there and sending that to your partner, you could then use your triple DES engine, use the same 8-byte key to decrypt that first round of ciphertext. And that would effectively recover your original clear text data. Then you could apply the same 8-byte key once again using DES encryption, and now you've got ciphertext that you can send to your partner. And your partner, if they're still limited to single DES, could simply use the first 8-byte key and recover your ciphertext, recover the clear text. So this was a very nice way to provide a transition from single DES to triple DES. However, as I got ahead of myself, you probably need to start looking at another alternative, the Advanced Encryption Standard. Let's go to slide 14. So again, the U.S. government decided that they needed to start looking for alternatives. They had a competition in the early 2000s looking for algorithms that could replace or could eventually replace DES and triple DES. There were a number of algorithms submitted. They were reviewed and analyzed, and eventually the Reichendahl algorithm was selected as the new standard. Reichendahl is based on the name of the cryptographers that submitted it for the competition. Now, AES is a little bit different in that it works on 16-byte blocks of data. Now, against those 16-byte blocks, you can apply different key lengths. You can use 128, 192, or 256-bit keys. If you use a 256-bit key, there are 1.1 times 10 to the 77th possible key values. So whereas NIST has said that triple DES will probably be secure until about the year 2030, given the pace of Moore's law and machines getting faster and faster, they've put no end of life on AES encryption. They haven't projected out as to when machines will be fast enough to do a brute force attack and basically try every possible key value, almost a Google worth of key values if you're using 256-bit keys. On the other hand, AES is similar to DES and triple DES in that it does kind of some of the same things in terms of substituting bytes, shifting rows around back and forth, mixing columns, and then applying the key value against the data. So it does some of the same type of arithmetic functions, but it is very different. If you encrypt data with DES or triple DES, you must decrypt it with DES or triple DES. If you encrypt data with AES, you must decrypt with AES. You can't combine the two and use both of them. So let's go to slide 15. A couple other things I want to talk about with symmetric. One is chaining. The original encryption algorithms use what was called electronic codebook mode or ECB mode. And the idea here was that you would take 8 bytes of data and apply an 8-byte key and encrypt that and get some ciphertext. And then you would go to the next byte or the next block, 8-byte block, and apply the same key. Now, the problem with that is if you encrypt 8 bytes of data with a key and then you encrypt the same 8 bytes in another block later on, you're going to get the same ciphertext. And maybe that isn't quite as secure as you'd like it to be. So if you have a text document with lots of spaces, lots of hex 40s, you're going to get the same ciphertext every time you encrypt those 8 bytes of spaces. Similarly, with the picture of tux here, if there's lots of repeating white space, there's lots of repeating black, there's lots of repeating yellow pixels, and if you just use ECB mode, your ciphertext maybe isn't going to be quite as secure as you would like it to be. So they came up with another technique called chaining, and this is kind of one of the art, the art part of encryptography that we talked about. Let's go to slide 16. So with chaining mode, what happens is when you encrypt the first 8 bytes of data, you're going to take the result of that operation, or maybe an intermediate result of that operation, and apply it to the next 8 bytes of data. So effectively what happens is when you get down to the last 8 bytes that you're encrypting, that's going to have been affected by everything that went on before it. So when you encrypt 8 bytes of spaces or 8 bytes of white pixels, it's going to get encrypted in the first block, and then that's going to be applied to the second block. So what you get out of encrypting the second block is going to be different from the first block. And if you apply that intermediate result to the next 8 byte block, you're going to get yet different results for that third block of data. Even if all 3 blocks were identical, the ciphertext of every one's going to be a little bit different. So as you can see from the encrypted picture of tux there, that provides much better security for your data. There's actually a number of different modes for chaining. The example here is cipher block chaining. You also have output feedback mode, a couple other variations of what data is applied or taken from the first operation and applied to the next operation. And I mention that just to say that the IBM hardware now, and even before the hardware supported, it was supported in software, it can support all of these chaining operations to provide better security for your data. Let's go to slide 17. The other thing I wanted to mention here that's new and comes with the Z13 is the support for a technique called format preserving encryption. So with the Z13 announcement, IBM said that the cryptographic hardware will support FPE mode. Now, what FPE means is that the format of your data is preserved in the encryption operation. So for example, there at the top, you have a social security number. It's a 9-digit numeric, and if you just encrypt that, you're going to get binary data. You're going to get, the example here is a hex 34 able 1 Charlie 902. So just encrypting the data creates binary data. It could be any one of each byte could be any one of 256 possible values. With FPE, your data, the characteristics of your data will be preserved. So that 9-digit social security number will be encrypted to a 9-digit number. Now that has some advantages when you're testing and upgrading your applications, in that if you have tests for is the data numeric, with format preserving encryption, those tests will still work, will still be valid. Similarly, the second example there is an address. You can set your application up and use FPE so that instead of encrypting the string there as hex data, it can preserve the format, and that numeric 123 will still be a numeric once the encryption is performed with FPE. And the character data there, the main street, is going to be character data as a result of the FPE encryption. Then the last one down there are PAN numbers or credit card numbers. Just like the social security number, a PAN is 13 to 19 digit numerics. And if you encrypt it without FPE, you're going to get binary data. So some of the checks that you could perform against that data would fail if you're using just straight encryption. With FPE, that that numeric digits will be preserved, and you will have numeric digits when you're done with the process. Let's look at that a little bit closer on slide 8. If you weren't aware, a credit card actually has several different fields in it. The first 4 to 6 characters identify either the industry or the bank that's issuing the credit card. And then, depending on whether you're using a 13 or a 16 or a 19 digit, that middle part is the actual account number of the credit card holder. And then the last digit is called what's a loan check value. And that is, you can perform some calculations against the rest of the account number and validate whether this is a valid credit card value. So if you apply format preserving encryption to a credit card or a PAN, you can actually leave the industry or the bank field the same. The account number that actually represents the cardholder could be scrambled, could be encrypted using FPE, and then that final loan check could be calculated against that new encrypted value. So it's performed against the 1234534819732 as opposed to just using the original loan check value. That way, that calculated loan check is a valid value for this ciphertext. So if your application is checking the loan check value, it will still work even though the credit card account number has been encrypted. So there's some definite advantages to using FPE. You do have to be a little bit careful with FPE. If you just encrypt some data arbitrarily using FPE, it may not be quite as secure as you'd like. For example, let's suppose you had a field that showed the sex of the account holder or the sex of the person associated with the record. If you just encrypt M and F, male and female, and use FPE, you're going to end up with 2 characters. Maybe the M is going to gets encrypted as an X, and the female is F is going to get encrypted as a Charlie. If you can just look at the data, since females make up 51% of the population, you can probably guess what the ciphertext is or what the ciphertext means in that case. So you got to be a little bit careful just arbitrarily implementing FPE encryption. There may be some attacks that can be mounted against it. But the IBM hardware does now support FPE, and on slide 19, so there have been various methods or algorithms that have been developed to do format preserving encryption. There are 5 different standards that have been submitted to NIST, the National Institutes of Standards and Technologies here in the United States, for implementing FPE. Now, there's links here, probably more detail than you want, but they all work a little bit differently, but they basically accomplish the same thing of preserving the format of the data in the ciphertext. And what IBM has announced with the Z13 is that they are going to support the VISA format preserving encryption algorithm in the hardware. Now, none of these have been accepted as formal standards. At this point, they're being reviewed and being evaluated. I keep hearing that real soon now NIST is going to make a decision, but I've been hearing that for a couple years. So can't really say when the formal standards will be announced and which ones are going to be chosen. But at this point, IBM has chosen to implement the VISA FPE on the Z13. So let's go to slide 20. Now let's talk about asymmetric algorithms. And these are a little bit different from symmetric algorithms in that they use 2 different but mathematically related key values, what's called a public and a private key. And the way the process works, if I want to exchange data with everyone on the phone, what I could do is create this public-private key pair value, this key pair. I could provide the public key to everybody on the call. Each of you could encrypt your own unique message to me using my public key, send it to me, and I can decrypt every one of those messages using my private key. Now, the guy next to you or somebody else on the call, if they get a copy of your ciphertext, they cannot decrypt your message using my public key. You must use the private key to reverse the process. Similarly, I could encrypt a message using my private key and I could send it to everyone on this call. Every one of you could decrypt that message using my public key. Now, that doesn't provide a lot of security for the message, but it does provide some integrity. You know that message had to come from me because you used my public key to decrypt the message. So, look down at the bottom, looking at the advantages and disadvantages, that public-private key make key distribution and key management simpler. Okay, to get messages from all of the people on this call, I only need one public-private key. Now, maybe each of you have your own public-private key, and you'll have to manage another key so that we can communicate with you. But the number of keys that I got to manage with public-private key encryption is much, much smaller than with symmetric keys. The downside of asymmetric encryption is that it's expensive. It takes longer, it takes more resources. You are not going to encrypt your database using public-private key encryption. You are not going to encrypt hundreds of thousands or millions of records using asymmetric algorithms because it's just too expensive. And we'll see a little bit more of that in a minute and why it's so expensive. Let's go to slide 21. There are basically three types of public-private key algorithms or asymmetric algorithms. RSA encryption relies on, and all three of these rely on what are called trapdoor functions. And by trapdoor, what we mean is it's very easy to perform a calculation in one direction, but it's very difficult or very expensive to reverse that process. So RSA encryption relies on factorization. It's very easy to multiply two numbers together and come up with a product. It's very difficult, given that product, to reverse the process and come up with those original two numbers that were multiplied together. Diffie-Hellman relies on logarithms. It's very easy to calculate e to the xy power, but given e to the x or e to the y, you can't reverse the process and come up with the other x or y value. And then elliptic curve relies on point multiplication. That establishes a relationship between a point and an elliptic curve, and it's very difficult, or it's very easy to pick a point on the curve and establish, or on the graph and establish a relationship to the curve. But given the curve, it's very difficult to guess what those original points were, the original xy values. So let's look at RSA a little bit closer, and you'll see how the math is pretty complicated. On slide 22, if we want to exchange data, the first thing we have to do is we have to come up with a key pair. We have to generate the RSA keys. So if I want to get messages from everybody on the call, what I would do is create a public-private key pair. And the way I do that is I start out by taking two prime numbers. And in reality, I want two very large prime numbers, two prime numbers that are hundreds of digits long. But for the example here, I'm going to keep the math simple, and I'm going to use the prime numbers 5 and 11. I start off by multiplying those together, and I come up with 55. And that actually is the first half of my key value. That's my modulus. Then I have to come up with an exponent, and I just pick an odd number, and it turns out that 3 or 65, 537 make good exponents. And they make good exponents because they make the math a little bit simpler. With those values, I can shift bytes or shift bits to do the math of dividing by 2. So in our example, we're going to select a value of 3. The odd number will be 3. And that's our public key, 55.3. Now, I've got to calculate the corresponding private key value. And my private key has to solve the, fit into the equation 1 equals d times e. The private key is going to be the d, mod p minus 1 times q minus 1. Now, I'm not going to go through solving that, but trust me that D is 27 in this case. 27 D times E, 27 times 3 is 81, mod 40, P minus 1, 11 minus 1 times 5 minus 1. So 81 mod 40 is 1, and that solves the equation. So my private key is going to be 5527. That's my public-private key pair. The private key, I'm going to lock away. I'm the only one that will ever see it, will ever use it. The public key, I'm going to make available to everyone on the call. So now let's see how we do encryption with that. On slide 23, if I want to encrypt a message, I'm going to use the message MFC. When I worked for IBM, I used the message IBM, but now I'm using MFC for mainframe crypto. So the first thing I need to do is I need to translate those character values into numerics. And for simplicity, I'm just going to use the letter of the alphabet. So M is the 13th letter of the alphabet, F is the 6th letter, and C is the 3rd letter of the alphabet. To encrypt each character, and again, this is very rudimentary. We would do more blocking. We're not going to do character encryption with RSA encryption. So this is just simplifying it so you can understand how it works. But to create the ciphertext or to calculate the ciphertext, I take clear text, the value, and raise it to the E power mod n. So for the character M, I'm going to take 13 to the 3rd power mod 55. That's equal to 2197 mod 55. The ciphertext for M is 52. For F, I'm going to raise it to the 6 to the 3rd power. That's 216 mod 55. The ciphertext for F is 51. Similarly, the ciphertext for the character C is 27. So my ciphertext is 52, 51, 27. Notice in that calculation, I only use the public key. I only use the values of 55 and 3. So now you've encrypted that data, 52, 51, 27, sent me that ciphertext on slide 24. To reverse the process, to recover the clear text value, I take that ciphertext, raise it to the value of D mod n. So for 52, 52 to the 27th power, see where the numbers, the math starts getting pretty complicated and might take a while. 52 to the 27th power is 2.1482 to the e to the 46th. Divide that by 55 and take the modulus, and you can run this through your calculator, we'll recover 13. Similarly, 51 to the 27th power mod 55 is 6th, and 27 to the 27th power mod 55 is 3. So I've reversed the process. I've recovered my original input of 1363, which translate to my original characters of MFC. Notice on the decrypt operation, I've only used the private key. I've not used the public key at all. So you can see the math gets very complicated. It's just using factorization, that trapdoor function to provide the security for your messages. But it will be very expensive. Now, asymmetric algorithms and symmetric algorithms are complementary. You need both. Again, you're not going to encrypt your database with asymmetric encryption. However, products like System SSL or the encryption facility rely on both symmetric encryption and asymmetric encryption. The data, the actual messages for both products are going to be encrypted using symmetric algorithms. But the key that's used to encrypt that data is itself going to be encrypted under a public-private key pair, and that ciphertext of the key value can be transmitted with the message. The partner can use their corresponding private key to recover the symmetric key and then use that to decrypt the data. Let's go to slide 25. Elliptic curve, again, relies on point curve multiplication, establishing a relationship of a point to an elliptic curve. And the reason elliptic curve is important is elliptic curve can use much shorter, smaller key lengths to provide the same level of security. The problem that we've got, especially with RSA encryption, is as crypto engines get smaller and smaller, think about a credit card or a smart card that has a cryptographic engine inside the smart card. As they get smarter or smaller, it's harder to get the sophistication in there. It's harder to get the electricity to the engine to be able to drive some of those calculations. So smart cards today typically use 1024 or even 2048-bit keys. Once we go to 4096-bit or even longer keys, you it's going to take seconds, if not minutes, to perform those calculations on a credit card size engine. So RSA is not really viable for some of those smaller engines. With elliptic curve, the key links can be much smaller, so you can get the same level of security with a shorter key and implement that on some of those smaller engines, those smaller technologies. So elliptic curve is the way of the future. Um, the US government has gone on record as saying that if you are doing public-private key encryption, you should be using elliptic curve technology. That is the most secure, the most feasible way to go forward. Let's go to slide 20. Turning our attention now to hashing, get away from the scrambling of data. Let's talk about the integrity of data. Hashing is an algorithm that will take an input message and generate a unique value that represents that message. So the example here is using a SHA-2 algorithm, SHA-256. And basically what you do is you take that message as input, you start shifting bits around, but at key points, some of the data you pull out and run through some of these algorithms that are documented here to create a unique bit string. So with SHA-1, whether your message is 10 bytes long or 10 meg long, it will generate a 160-bit thumbprint that represents that message. For SHA-256, the thumbprint is going to be 256 bits. For SHA-512, the thumbprint is going to be 512 bits long. And those bits simply represent that message. Now, let's go to slide 27. Now, the way a hash works, or the way a modification detection code works, is I'll take my message or my input data, I'll run it through the hash algorithm and generate that hash that represents the message. I'll then send you the message along with the modification detection code, the hash value. You run the message through the same hash that I ran it through, and if you come up with the same modification detection code value that I sent you, you know that the message has not changed in transmission, that there weren't bits or bytes dropped in transmission, either deliberately or accidentally. So you have some confidence that the message is as I sent it. Now, there are three characteristics of a good hash algorithm. First, it's a one-way operation. That is, if I take whether it be a 10-byte message or a 10 megabyte message and run it through the hash algorithm and generate a hash, you can't take that hash value and recover or recreate the 10 byte or the 10 megabyte message that was used to generate it. You just can't reverse the process and come up with the original data. Second, it's hard to find a collision. That is, it's hard to find two messages that would generate the same hash value. And certainly you can't just tweak a message and change a bit or byte and not change the modification detection code. It's just statistically unlikely that any two messages will generate the same hash value. Now, the reality is that by reducing it to such a, reducing a 10 megabyte file to whether it be a 256 or a 512-bit hash, there are going to be collisions, but it's statistically unlikely that you can find a collision that given a hash value, a particular hash value, you would have a difficult time finding a message that would generate that same hash value. And then the third characteristic of a good hash is the fact that the hash does not reveal any information about the original message. So if you've got a hash value, you can't look at that and say, oh, the original message was character data, or it was decimal data, or it was this long. The original message was this many bytes long. The hash value doesn't reveal any information about the message that it represents. So with that, let's go to slide 28. As I mentioned before, changing a single bit or a single character in the message will change the hash. So this is an old example. I used the SHA-1 algorithm and I hashed the message. The quick brown fox jumps over the lazy dog, and I get this bit string that starts with Able 9. I changed one character. Instead of jumping over a dog, we're now jumping over a hog. Look how different. Even the first byte of data is different in the second message. So it's very difficult to come up with a collision, to come up with two hash values that would represent, or a hash value that would represent two different messages. And don't confuse a hash with Hormel hash. Let's go to slide 20. If I apply a key into this hashing algorithm, I provide a little bit more security, and this generates what's called a message authentication code. Once again, what I would do is I would take my data, my message, I would run it through the hash algorithm with the symmetric key as part of the input and generate this message authentication code. I would send you both the data and the MAC, and you would already have a copy of the key, but it just uses a symmetric key that we share. You can run my message through the same hashing algorithm with the same symmetric key value. If you come up with the same message authentication code, you know not only did the message not change, but it had to come from me because you and I are sharing that symmetric key value, and it would have to come from the partner that's sharing that key value with you. And then on slide we'll look at digital signatures. Digital signatures basically combine hashing and asymmetric encryption. So what happens with a digital signature is you take a message and you run it through a hash algorithm to generate a hash that uniquely represents that message. You then apply asymmetric encryption, public-private key encryption, to encrypt that hash value, and that's what's called a digital signature. So on slide 31, digital signatures are used in digital certificates. Now, the idea here is, let's go back to the example where I want to get messages from everyone on the call. What I have to do is I've got to get my public key to all of you, and I've got to get it to you in a way that you know it's my public key so that you know that it's me that you're going to be communicating with. The way we do that is with something called a digital certificate. So once again, I would generate a public-private key pair. The private key I'm going to lock away. I'm the only one that's ever going to use it. The public key that I need to get to you, I'm going to package into something called a certificate request. Certificate request I'm going to send to a certificate authority. Now, what's in the certificate request is some information about me. So it's got my unique name that uniquely represents me. So it's got things like a name. It's got like the company I work for, the location. You know, am I based in the United States or another country? So there's some uniquely identifying information in there. There's some date values, things like expiration dates of how long this certificate, how long this public key is good for. There's version information. What version of public-private key is this? There are algorithms. You know, what algorithms did we use? What hash algorithms are we going to use as part of this process? And then there's the issuer name. That's the certificate authority that's going to do some validation. And then there's my public key that I need to get to you. Now, all of this information is in the clear. I send the certificate request to a certificate authority. The certificate authority, the first thing they're going to do is some due diligence and validate. Is this really Greg Boyd's certificate request? Is this really Greg Boyd's public key? A couple years ago, there was a situation where some bad guys sent a certificate request to a certificate authority and said, hey, we're Microsoft. Please generate us a certificate. And the CA did not do the due diligence, so these bad guys were able to masquerade as Microsoft. And you know, when it was realized, the certificate authority had to go back and invalidate the certificate and all. But what you're paying for when you request a certificate from a certificate authority is somebody that's going to vouch for and validate this really is you and not somebody pretending to be you. The certificate authority, once they've done that validation, they're going to take that certificate request and run it through a hashing algorithm and generate a modification detection code. That uniquely represents that message, that certificate request. They're going to take that hash and encrypt it with the CA's private key. So the encrypted hash is a digital signature. That's going to get appended to the certificate request, and that's the certificate they're going to send back to me. I can then turn around and send that certificate to every one of you on this call. Now, when you receive that certificate, what you can do is strip off that original certificate request, the front end, and run it through the same hash algorithm as documented by the algorithms in the clear, run it through the same hash algorithm and generate a modification detection code. Then you'll strip off that digital signature and decrypt it using the CA's public key. If those two values match, you know you have my public key in this certificate that was validated and vouched for by the certificate authority. Now, where's the CA's public key? How do you get access to the CA's public key? That's built into a lot of systems. So IE or Firefox, whatever browser you're using, if you go look at your internet options, you will see that there's probably hundreds of public keys that are predefined and built in as a part of Internet Explorer or Firefox. Similarly, when you install RACF, the RACF database comes pre-populated with a whole bunch of public keys from certificate authorities. Now, in the RACF world, you have to go in and trust and flip a bit to say, I trust this certificate. I want to be able to use this certificate. But they are built into systems, whether they be browsers or the RACF or Top Secret or ACF2 environment. So you have access to the public key so you can decrypt that digital signature that the CA has provided as part of the digital certificate itself. Let's quickly slide 32, pin functions. As already touched on at the beginning, a pin function or a pin can be up to 10,000 different values. So it's not all, it's easy to do a brute force attack against the pin value. So over the years, there have been a number of standards and ways to protect pins. So you start off by actually embedding the pin in what's called a pin block that has some other information in it. So you're not just encrypting a 4 numeric digit value. There's a number of different pin block formats that have been standardized. All of these are supported in the IBM Crypto Express hardware. One of the requirements for pin processing is that it be done in a secure tamper-resistant environment using tamper-resistant hardware. So the Crypto Express cards from IBM provide that. These standards have been implemented. You can use those Crypto Express cards to recover your pin values. And let's go to slide 30. We're going to kind of wrap things up here. I want to quickly talk about some of the information that came out with the Z13 announcement. I guess the biggest thing on there is the fact that there's a new Crypto Express card. The Crypto Express 5S is presumably going to replace the 4S. Now, jumping down a little bit, also in the announcement, there's a new TKE version 8, and it's actually described as the 4767 TKE. And that kind of hints to me that there is a new cryptographic chip that's going to be implemented on the Crypto Express cards. Going way back, the 4764 was implemented on some of the older Crypto Express cards. Then we had the 4765. Now we've jumped to the 4767. It looks like the Crypto Express 5 card is going to be built on this new technology. Now, one of the things that's been added on the Crypto Express 5S is greater than 16 domain support. So the announcement letter talks about the fact that you can support more than 16 domains. If you remember when we talked about hardware before, each Crypto Express card can support up to 16 LPARs. Well, that's been a pretty serious limit, and so IBM is expanding that limit, And in the IBM Z13 technical guide, the draft red book, it actually talks about being able to support up to 85 domains. So it looks like you might have each card will be able to support up to 85 different LPARs. Hopefully more documentation will come out on that at GA. The, both the CPAC-F and the Crypto Express 5S have improved performance characteristics. Specifically, it talks about doubling the amount of throughput with large blocks of data. So expect the IBM white paper, the performance white papers provide a lot more detail about just what operations are faster and how much faster they're going to be. Back to the TKE, another capability that's going to be that's been introduced on TKE 8 is print capability. Customers have been asking for some time for the ability, okay, when I create a key on the TKE, I want to create a hard copy of that key just to be safe, so that in an emergency, I've got the key value, and if I had to, I could go do the calculations by hand. It looks like they finally introduced print support so that you'll be able to print some of that. Now, I don't know all the details about which printers and all are supported, but there is a print capability. There's some new master key management. I think they're making the process even simpler for loading master keys using the TKE. There's going to be FIPS certified smart cards. The Crypto Express is FIPS certified. The smart card readers were FIPS certified, but the smart cards have not been certified up to this point. It looks like now they're going to provide smart cards that are FIPS certified. And then the other interesting thing in the announcement was it looks like that if you have a TKE 7, you can upgrade to a TKE 8. There's a feature code in there that talks about if you order the feature code, they'll ship you this new 4767 card that you can install in your TKE so you don't have to buy a whole new TKE. You just buy the new card and the new lick that will run TKE version 8. And then finally, there's a new version of ICSF that's available that will support all of this new functionality that will be able to support up to 16 or up to 85 domains and support the new capabilities that are going to be on the Crypto Express cards. Down at the bottom, some reference materials, the actual announcement letter, and then a couple references to draft versions of Red Books that talk about the new technology. I'm sure there will be a lot more information coming out, especially at GA. So with that, we'll things up with some references. If you're looking for some just to read about cryptography in general, I recommend that second one, The Code Book by Simon Singh. Very reading, provides a lot of background information about cryptography. Um, the free stuff there, Bruce Schneier is the industry pundit that I referenced a couple times. He publishes a monthly newsletter called Cryptogram. He just left. He was working for British Telecom. He just left there, but I presume these monthly newsletters are going to continue. On slide 5, the ICSF manuals. If you're migrating from ZOS 1 dot whatever to ZOS 2.1, just be aware that the manual numbers have changed, so you need to make sure you get the correct manual number for the version of ICSF that you're running. And with that, I'm going to turn things back over to Jerry and let him open things up for questions. Thanks.